Calculating standard enthalpies of solution, or the delta H of a solution, we can determine enthalpies of basic solutions. Remember that a basic solution in our class is when an ionic salt typically is dissolved in water. During that process, some salts, when dissolved in water, will cause more energy to be released in an exothermic process, whereas other salts are going to absorb or take energy out of the surroundings, causing more energy to be absorbed in an endothermic reaction. That's the basic premise behind an instant hot pack, where those types of salts give off energy, making the surroundings hotter, versus an instant cold pack that absorb energy or take energy out of the surroundings. It can also help explain why certain salts are conducive for melting snow or ice, say during like a snow or ice storm. There's more to that story too, but that's one portion of that story. You want to choose a salt that's exothermic that helps melt the surrounding water. Okay, now when we calculate an enthalpy of a solution, we want to express it in units of kilojoules per mole, so joules might have to be converted to kilojoules. We'll use the same reaction equation of Q equals MCAT, where M represents the solution mass. That's not just the water, but it's the water plus the solute. C represents the specific heat capacity of water, and the measured temperature change is that of the water. When a solution is created, you can kind of think of it like two different steps that happen simultaneously. When we break those steps apart, here's what's taking place. A salt crystal that consists of positive and negative ions bonded together with ionic bonds exists in solid crystal form. Before it's dissolved, those ions are bonded together. Now, after they dissolve, they have to be broken apart. And so, in order to break those negative ions away from the positive ions, energy has to be taken in. So, that's a positive delta H value as energy is consumed to help splice those bonds. Once those bonds are spliced, now they're going to be surrounded by the water particles through hydration. When they're hydrated, they're actually stabilized and energy is given off. So, where bond breaking requires energy to be absorbed, bond forming stabilizes things and helps energy to be released. And so, depending on how much energy it takes versus how much energy is released, we're going to have an overall analysis of positive versus negative energy, and we can classify them as exo or endothermic. You should bear in mind during this hydration process, just to tie it back to previous units, that opposites attract, and the negative ions are attracted to the partial positive end of water, and that would be the hydrogen, less electronegative side, whereas the positive charged ions are attracted to the negative side of the water. That would be the more electronegative atom, or the oxygen side. Nevertheless, when we take sodium chloride, 1 mole of it, into a solution, it would take 774 kilojoules of energy to splice those bonds. But then when those same ions are hydrated, 770 kilojoules of energy would be released. Overall, the salt particles gain 4 kilojoules of energy, but the water would lose 4 kilojoules of energy. So from start to finish, if the water is losing energy to the ions, there's going to be a temperature decrease. And so we'd classify this as an endothermic reaction. Finally, let's get a little bit of practice. Let's calculate an enthalpy of a solution, and our first one's going to be sodium hydroxide. A student adds 4 grams, my apologies, of sodium hydroxide into a coffee cup calorimeter, and there's 100 grams of water in the cup, and the temperature of the water after the dissolution process goes up by 10 degrees Celsius. Okay, that would be an exothermic process as the water goes up in temperature. With an exothermic process, that will be a delta H of solution that has a negative sign. Let's bear that in mind at the end of our problem. Now, assuming that the cup is very well insulated and that water's heat capacity is 4.184, we can determine the enthalpy of the solution of sodium hydroxide in kilojoules per mole. We're going to use Q equals the M of the solution times the C of water times the delta T of water. That's going to involve 100 grams of water plus 4 grams of salt for a 104 gram solution to be multiplied by 4.184 joules per gram degrees Celsius for the heat capacity of water times 10.0 positive degrees of water as it gains temperature. When we multiply this out, we're going to get a value of, let's see, 104 times that times 10. 4,351.36. That would be joules as grams are canceled and Celsius degrees are canceled. We do want to convert this to units of kilojoules. So we'll divide by 1,000 joules in 1 kilojoule. Or we'll get 4.35 kilojoules of energy during this dissolution process. Now that's being taken in by the water as it escapes the system. Okay, and because of that, what we're actually going to do here is we're going to flip the sign, because the delta H value is written from the perspective of the ions, not from the perspective of the water. So as the water gains the energy, the salt is actually losing energy to the water, or the ions that exist in the solution. Now, with that being said, we're going to divide that by the total number of moles that was put into the solution. Well, we can't divide by 4 grams, but we can divide by the number of moles that 4 grams represents. So let's do a quick conversion here. Okay, 4 grams divided by the molar mass of sodium hydroxide, which is 40 grams, is equal to 0.100 moles. We will keep 3 sig figs. Finally, we're going to take our amount of energy that's released from the system to the surrounding water and divide by 0.100 moles of sodium hydroxide. That way we can express our units in kilojoules per mole of salt. That's the standard way of representing delta H of solution values. Negative 4.35 kilojoules divided by 0.100 moles of the salt is a delta H of solution equal to 43.5 kilojoules per mole of sodium hydroxide. And it's important that we strike in our negative sign because this is an exothermic release of energy. And that is it. Thank you.